Okay, I don't think that we should waste any more time of the people who decided to join in on time. If anyone else joins, I will admit them. The link is open for anyone to join at any time, but I think it's rather time to start now. I will be very brief in my introduction. We are starting a new initiative, which is called Skopje Tech and Talk. Although the name suggests that it's related to Skopje, the idea is that this initiative is more or less original one. We want to promote different topics related to technology and specifically software development. Topics that there are not current groups that naturally support them, maybe topics that are interesting and not exactly software development, but maybe more business analysis and business development related strictly to the technology that's used nowadays. And in order to start with these sessions, we decided to start with something, as I would say, a little bit more boring, with the title Concurrency in Spring Boot Projects with Examples, which is something that I really didn't thought that there will be much audience for. But as Gjoko said, I'm pleasantly surprised. We already have 32 participants. Gjoko Kostadinov will present himself and will talk a little bit on this topic, and after that he will stay a little bit longer to take some questions. The rules of the game are you're not allowed in this meeting to unmute yourself and to show your video, just to keep things more simple. If anyone wants to ask a question, as I wrote down in the chat, please use the chat. If anyone wants to do that in person, just write a message to me in the chat and I will unmute you when the time is right. So we just want to leave Gjoko to present without a lot of disruptions. So Gjoko, whenever you're ready, the floor is yours, and I will just switch off my camera so no one is distracted by my beautiful face.
Thank you, Gora, and your beautiful face, if I may say so. So, hello to everyone. Thank you for attending such a number. 32 is, I would say, interesting number in our world, in our profession. So, to start, I would like to introduce myself. I'm Gjoko. I work in Scalefocus. I'm principal software engineer, whatever that means. I have had a lot of sleepless nights here in this firm and in others regarding this topic, and I think that I have a couple of things that you might find interesting. At the moment, I work at Scalefocus. You might know our firm, the firm that created the census software for the census in Estonia that everyone loved and supported and approved. And unlike that, today we're not going to count people, we're going to count threads. So let's start with concurrency in Spring Boot. Let's start with a simple definition. So what is concurrent programming? Concurrent programming means doing more than one thing at a time, which is not the same as a parallelism. But you could say that actually parallelism has more than that. Actually, parallelism has a kind of a subset of concurrent programming. And with that in mind, let's go to the next slide. Now in Java, we all have heard of the two main paradigms that are related with concurrent programming, and that's a thread and a process. What's the difference? A thread is a lightweight process and has its own stack of data and shares the data with other threads. And every thread has its own memory cache. And all the data is stored in its own memory cache. And a thread can reread that shared data that can be modified by other threads. Or also, at the same time, thread can have data that's thread specific. On the other side, a process is the JVM machine that we all know that runs independently and isolated of other processes, and cannot access actually the data that's occupied by other processes and has its own CPU and memory allocation via the operating system. And as I mentioned, the Java application is such example. Now, we came here to talk about concurrency. The main question is when we talk about concurrencies, how many times can we speed up a program? And that question has been already answered for us. Basically, there are two different laws by definition. One is Amdahl's law, and the other is Gustafson's law. Amdahl's law says that if the F is the percentage of the program that cannot be sped up, the serial part of the program, and n is the number of processor, then this is actually the biggest speed that we can achieve with respect to speeding up the program. So basically, the speeding up of our program is directly related to the percentage of the program that's parallel, that can be parallelized, and the percentage of the program that cannot be parallelized. On the other side, we have Gustafson's law, which is actually kind of an improvement. What's the difference between the two? Gustafson believed that the times needed for parallel execution is fixed, while the time for serial execution is bigger depending on the number of processors. And he actually implemented another formula, as you can see on the screen, but we're not here to discuss mathematics. So keeping these two in mind, we continue on. Specifically with Java, when we talk in regards to multi-threading, these are the main keywords that come in mind. And we will discuss each of them individually and a little bit more in detail. Starting with runnable. Runnable is an interface. What does it mean? It means that it cannot have its own implementation. In order to create a new thread, we gotta implement, as we can see here, we have to implement the interface. And after implementing, we have the run method, and we can run that new thread. That we can create a new instance and then run the new thread. On the left side, we have the same example, as you can see, with Lambda expressions. So basically, we can create inline anonymous implementation of the class and reuse the Lambda. Actually, the two pieces of the code are the same implementation. After runnable comes thread. Thread is a solid implementation and can be instantiated as such. In order to use the functionality of thread for creating new threads, we have to extend the class. As opposed to implementing runnable, we're extending thread, but this is very basic stuff. And basically, it's the same thing. We implement the thread, then we create a new instance for the thread, and then we start the thread itself. Continuing on, after those two, next in line is synchronized. Now, synchronized, there are 5, I would say, mostly used and mostly known types of implementations. We can synchronize instance methods, we can synchronize static methods, and we can synchronize instance and static code blocks. And also we can synchronize inside a Lambda function. As we can see, this is a plain method without a synchronization. Then we have the first implementation where we use the keyword synchronized, which is a reserved word in Java for synchronizing this method. The next one is the synchronization of static implementation of that method. And after that, we have the additional synchronization of a code block inside a method. And then we have a synchronization of a code block with a static method as well. Now, if we have synchronized a piece of method, that means that that chunk of method will not be accessed by more than one thread at a time. But this comes with a downside because this means that we are losing memory. We're losing, I'm sorry, we're losing execution time because the threads are synchronous at this moment. And we also lose additional memory because we have to keep internally, the JVM has to keep the lock itself. So it has mainly it has the time overhead. And it also means that if we have a piece of code synchronized, it doesn't mean that it's actually completely thread safe. And of course, the last that I mentioned is synchronization on the base of Lambda function. It's basically the same as synchronization within a code synchronization code block inside an instance method. Moving on, the next and actually a little bit newer machinery that's used in concurrency is the completable future. What's interesting about the completable future? The interesting part is that it's part of functional programming. So actually it's very easy and elegant, to say at least. And it has a couple of inbuilt functionalities that can give us the ability to create easily async methods, call those methods and manipulate them. As we can see from the last example, which I ordered in backwards, we have completable future that actually does nothing async. It just returns the word hello, but you can imagine here that we have some kind of execution like calling to fetch some data or to persist something or to dispatch a message to a queue or a push notification. And all of that can be implemented in this simple way. We just need to have the method itself and then just execute it from here. When calling the code from here, we'll let the execution continue and we actually don't stop the main thread. This offers the advantage of executing code that will actually not block the main thread, which means that we'll have faster execution time. But of course, this is not a universal solution. So in case we need to wait for some call to execute and return the result, this will not do us the job. Other than that, I would say that we also can have completable futures, future that can be chained. Like we want to execute some other piece of code after the original completes, which means that that's actually the part of functional programming that we see in mind. When I say functional, you will probably remember instantly about streams and lambdas. This is something like that. In that, as you can see in this example here, we have completable future that has supply async, and after it returns the completable future, we can then chain another method, which again can be another call, and then apply where we can execute different kind of method that will wait to for the first method to finish and then for the second one to continue. And the third one is the completable future can be used with cached thread pool. We will talk about executors a little on later, but I thought that this was a relevant example here. As you can see, we're using the completable features and we can call them inside the executors. And this is basically the correct way, one of the more elegant ways to use them. One of the other functionalities the completable features offer is the combining features. We can choose and adjust the behavior of the features. And let's say we need to fetch some data, and then we need to wait for the data to be fetched. And after that, we need to make 2 REST calls and get the results from those calls. Completable features can do this very elegantly. where we can first call the completable future, then apply, and then we can chain the other two with supply async, where we throw one of the call, then wait for the result and call the other with then compose, which means that after the first one is finished, the second one will be executed. What's the difference between then compose and then combine? The difference is that in one we get the computable future as a callback, while in the other one we work with the first computable future that we have used in the first async call. But on another note, if we don't want to use if you don't care about the either one of them executing, we can call both and then just use accept both. And after accepting both, we can do some other logic like get the results or maybe do another call. And this is one of the examples of async invocation combined with the power of functional programming. Now going back to something more primitive, the word that I find interesting is volatile. Volatile, although not so mentioned and often encountered keyword, is probably very used. Is very used if you sometimes have the need to dig deep in some library in order to understand the curious or unwanted execution of your code. What's the difference between what's volatile used for? Volatile is a keyword that makes sure that every word, every thread reads the latest copy of the execution of a thread. Basically, if thread 1 comes in and makes some changes, if the metadata or the field is volatile, is marked as volatile, then that means that when thread B comes, it will read it directly from main memory as opposed to the CPU caches that the threads use. And this will guarantee that we won't have race condition and that every thread will have the latest data regarding this property. But this again comes at a cost with that reading from main memory is slower. So this will slow down the execution of the two threads. And also it means that it will cost additional memory because persisting the field or the value of the field on the main memory actually will cost more. And this is something that can be ignored when we talk about small chunks. But if we have to iterate or operate over a large data set, like millions or hundreds of millions, you can quickly deplete your memory and have curious errors popping up in your stack trace. And the fifth is principle that I would say we have often encountered it, but we rarely think about it. It's the immutability. Actually, it contains several of the object-oriented principles, which is the encapsulation and inheritance. And why is that? Because the immutability as a principle means that if you want your data to always be thread safe, is to make the data itself, the data field, private, to avoid creating setters, and uncopying to copy the entire data in the constructor and avoid changes outside of the data. Another is to never directly return or expose the data to a caller, and not change, or if change happens, should not be visible from the outside. Now, it might sound strange to you, but if I say to you array list, you all will remember that actually we get the array list, we have setters and everything, but we actually never have, we cannot touch the data inside. We only call the setters and the operators on the array list, but we never actually have any freedom to manipulate the data. And this is one very simple example of this kind of immutability. Now moving on to a more complex and more interesting topic, I would like to say a few things about thread pools and executors. I would say that there are four main types. On the right side, you can see the main idea behind the executor service. We have task submitters, which is actually when we define different completable futures or asyncs or whatever on the left side. Then we put them inside the queue and we call the thread pool executor to execute the different tasks in different calls, and this does not block the main thread again, and this permits us to do to execute things in parallel and concurrently. There are different methods already implemented in Java on this topic. Those are the executor and the executor service, the thread pool executor, the scheduled thread pool executor, and fork join pool. Now I'm going to present an example on each of those. This is an example of the executor. Executor is the interface that we use. Actually, all the executors implement this interface, and this enables us to have decoupling from the concrete implementation of the executors. As we can see, we can implement it with a single thread executor where we want to run one thread in async and continue with our flow or return something to the user. For example, the user wants to submit a message to the SQS. After receiving the message, after taking the request, we can fire this executor service, which will have the logic inside to push the message to the SQS and then immediately return. And we wouldn't care if the about the time it takes for the executor to push the message to the SQS or RabbitMQ service, whatever we use as the implementation, and this would speed up the processing. Second one is the executor service. As you can see here, we can we can define the number of threads we want to execute. Keep in mind that when executing with a certain number of threads, you're again working with memory, so you gotta make sure that you have enough memory allocated to the JVM and actually enough memory outside of the JVM. The third one is the thread pool executor. Again, with the thread pool executor, we create a fixed pool. Nothing special here that can be said. And also, I would like to mention the cached thread pool. The difference is that with the cached thread pool, the number of threads and the memory are stored separately as opposed to the thread pool. Moving on, we have scheduled thread pool executor. It's on the right side of the image of the slide. As you can see, we can define the number of threads we want, but we also can define a delayed start. What this means, it means that we can use this thread pool after a certain time. Where does this come in handy? For example, let's say we have some Spring Boot project where we need to execute some kind of logic, and that logic involves part of the Java beans, part of the services that are defined inside Spring as beans. Now, if we execute this logic from the beginning, it's very likely that not all of our services will be instantiated, and not everything will be available, and because of that we'll have a problem. We can use this logic to delay the start of the thread pool executor service, so that we will be sure, for example, like after 1 second or 2 seconds or maybe 10 seconds, the entire service will be started and everything will be available and the logic can be executed. And the last one, and in my honest opinion, I have never found this while working with thread pools or executors of any kind, but it's interesting. It's fork join pool executor. The fork join pool works on the principle that it solves the problem when executing a lot of tasks for recursive methods and recursive calls. For example, if we want to, if we have some kind of recursive structure like the one on the left side of the slide, and we need to do some async or time-consuming tasks, what does the fork join pull does? When invoked on the main starting point, it will go through the tree, define all of the pools, and when it comes to the outermost executor tasks that are executable, where we don't have any more references, but we only need to execute tasks, then it gets, it defines all the tasks, like going through a tree. When it comes to the outermost leaves, it counts all of the tasks and then creates a thread pool and executes tasks in parallel. This is part of the divide and conquer strategy. It's an implementation of the such, and it's I believe that I have read that it's used in some use cases in Hibernate, and also maybe some use cases where we have graph-related databases. But I have not dived under the hood in both of them. Okay, so moving on. The name Spring was in the title, so it's time we came up to Spring. Spring-based executor service is pretty standard. As you can see, the only difference is that then after defining the after defining the thread pool task executor, we can set the core pool size, the max pool size, queue capacity, for example, also the thread prefix, and then we return it as a bin. And after that, Spring Boot uses it as a off-the-shelf under the hood. And keep in mind that here we have to use the enable async on the application itself so that we can enable this kind of functionality. And also we have to annotate the method inside the service that we want to use as an async. Moving on, another thing that I would like to mention here, until now we mostly talked about parallel execution, which is a subtask of concurrency. But when we think about concurrency is basically doing things in different things in parallel. So one of those things would be scheduling. While the main threads are processing, let's say, incoming requests, there are also another threads that are doing some async stuff, like cleaning up that data, or copying data from one server to another. And this can be done with, of course, scheduling. In order to use scheduling, we have to use enable scheduling annotation on the Spring configuration, one of the Spring configuration files. And we also need to use enable async. As we can see from the example here, when we use enable async, the scheduled can be used with a fixed rate, which is actually time. We can also use it to schedule fixed delay, and also with initial delay. Again, same as the scheduled thread pool. We have initial delay, which can help us in similar use cases where we need to wait before we start to periodically execute some piece of code or some functionality. And the last one is a cron job. Here, the cron is actually followed with a cron expression that actually allows us to define how many minutes in the day, on how many hours, how many days, and I think how many milliseconds, but I'm not really sure because I haven't used cron in a while. But having that in mind, it basically allows us to define the behavior itself. And for example, if we want to, we can actually define it so that, for example, we run our cron Monday, Tuesday, Wednesday, Thursday, Friday, and then skip Saturday and Sunday if we have that kind of need in our functionality. Also, as you can see here, I have commented out that we can actually use a Spring-based interpolation of the values, which can be defined in properties files. So this is quite handy, and we can use this to define the behavior of our cron jobs, of our scheduled jobs, without the need to recompile the code if we just change the value in the properties file. Again, the last thing about scheduling is that we can also do it dynamically at runtime. As you can see here, we have the scheduled task configurer. Here we can actually configure the task executor that will execute the scheduled tasks. And also we have configured tasks method, which is already given by the scheduling configurer interface, where we can define the tasks themselves and define when the next execution time will be, and apply different logic, where, for example, we can read this property from third-party servers or from database. This will allow us to create a functionality that is like Zookeeper, where we can read the property files from third-party places, and this has actually come quite handy in the past. Another thing that I would like to mention is that a lot of time when we talk about concurrency, we cannot avoid talking about working with messaging. Spring Boot has a very powerful messaging functionality, which is the JMS listener. I have actually used this quite a lot, and it does come quite handy when we have dynamical payload and we have unpredictable data. What does that mean? For example, it means that we want to define, we have the following use case. We have a JMS listener that wants to listen on a queue. Now we don't know when and how big the number of messages will be that will come into the SQS queue. And in order to handle this, we can use the concurrency mechanism. What does this mean? This means that at start, the JMS listener will fetch, will start only one consumer on the thread. And when new messages start to arrive inside the queue, the JMS listener will notice this and will scale automatically. This comes very handy if you are using, for example, cloud. I have used this for ingestion of messages from SQS while deploying the Java application on EC2. And what we did in our case, we used a very similar functionality. And we also created scaling on EC2 side based on, now we're getting a bit off topic, but I think this is interesting. We were scaling based on CPU utilization. And basically, I had a task where I had to go in, pump in the queue, and see how much CPU, how much core units, and how much memory we needed to give to each of the tasks on the EC2 service. And after doing that, what we did was actually define the EC2 service to scale from, let's say, from 2 to 4. So this meant that we had 2 JVMs consumers running initially, and when the messages came, each of the JVM of the consumers actually started scaling up to 4 consumers in parallel. What this did in the background, it pumped up the CPU, and when that was pumped up, that was the trigger for EC2 to spawn more Java threads and more containers, and basically that's how we had very fast scaling based on our needs. Now, after that, I think that it's time. I think that we talked a lot of Spring Boot. Now it's time to talk about something that's more new and not so much used. Actually, it's not so much new as it is recycled, if you ask me, from a different paradigm, and that's reactive programming. Now, in reactive programming, Spring Boot has a new project that's called, actually it's not very new, but it's rather not old, I would say. It's called WebFlux. What is WebFlux good for? Actually, it changes the entire paradigm on how Spring Boot works. Until now, Spring Boot had, if we take the old Spring Boot projects, they had blocking threads and blocking IO. And what it meant that we had to have a lot of, when traffic came in, we had to have a lot of threads running in parallel, and all of them or most of them were blocking, and that's how the logic was executed. On the left side, we have a traditional Spring Boot logic diagram. When the requests came in, after they are handled from the thread pool, then available thread was dedicated to the request handler, and then we would call a blocking source, which meant probably calling a third-party service or communicating with a database or both, and then actually go back and return the response until the response was returned to the initial user. Now, on the left side, we have something that's with WebFlux, which is a bit different. Again, we have a thread pool, and we allocate new thread for a new request. But then the thread registers create a callback and register that callback, and then return the response immediately, which means that the thread is non-blocking. And when the response comes, it renews the thread, and we actually return the response from the blocking source back to the user without creating a blocking thread while waiting for the blocking resource to execute. This is the diagram defined more in depth. As we can see, when the request comes in, there is an event with callback with fixed number of small threads that constantly look for event pool. If you see, this is, if some of you have used it, this is very similar to what we use in Kafka or another messaging service where we constantly listen for new messages. And then when the event comes back, the response comes back from the DB layer, we return we again allocate a new thread because the old one was closed, and with the new thread we return the response back to the presentation layer or the controller layer in Spring. This is actually the WebFlux logic for the scenario where we use this for concurrency. And there is one additional problem, which is that what happens, we have a event loop, but what happens if in that case we have something that is blocking? Well, in that case, if something that comes blocking, we use schedulers and we use async tasks, and so that we make sure that the event loop is never blocked and it's never throttled by one or few events or methods. And this sounds very interesting and promising, but again, everything has pros and cons, I would say. I'm sorry, and everything has its own drawbacks. For example, if we use this kind of methodology, in my opinion, we would have to sacrifice transactions, which I think that not a lot of people actually appreciate how handy and life-saving transactions are, at least in the sense of traceability and in the sense of executing data and in the sense of keeping all data up to date and preventing race conditions in a lot of places. So that's one thing. Another thing I would say is that this technology is actually very promising, but has not had its mettle tested against strong loads or loads that are quite big, as opposed to the traditional Spring Boot project. But of course, this is much more suitable if we care about limited resources and reducing the number of memory and threads used while working with Spring Boot. Okay, so let's dive a little bit deeper in the reactive classes. Basically, we have two main classes. One is the mono and the other one is the flux. What's the difference? The difference is that the mono is a class that returns binary result. It either returns one result or none, while the flux can return a number of results from 0 to n. So mono is like binary and flux is continuous. That's how I would describe it. This is a sample repository, Mongo repository, how it would be defined with reactive programming. As we can see, we have reactive Mongo template, and the other stuff is pretty much already seen with the port and the DB name, and the creation of the client. Moving on, this is how how reactive endpoint looks like on the front end. And as you can see in the response entity, we can return either mono or we can return flux, depending on if we are looking for example, one entity, or we're looking for all of the entities or more than one entity. And again, we come to the pros and cons of the concurrency and the synchronization. I would say that pros are the improved utilization and faster response, while the cons are that it has increased resource consumption because spanning more threads and doing stuff in parallel costs resources. Because we want to save time, we'll have to sacrifice computational resources. Also, there is a lot of context switch overhead. We're not thinking about it, but even the main thread has to switch context when different responses from different asynchronous events have come in order to redirect them to the to join them to the right thread and to continue with execution. Also, it has increased complexity of designing, coding, and testing. God knows that debugging and even doubling with problems like that in an enterprise application can be very tricky and can lead to a lot of sleepless nights and a lot of coffee drank. So another thing is that it can lead to race condition and critical section. What does that mean? It means that you can get a race condition. For example, I had that problem when I was trying to use DynamoDB, and we had a lot of Java applications that were trying to increment a counter. And because everything was done in parallel, and at the same time we didn't actually use the atomic write units, and also we didn't use consistent write units, we had problem with this. I have encountered the same problem with race condition when trying to persist something to disk. So keep in mind that this as well can be a problem when using multiple parallel threads. And also, it's a good advice to not parallelize or do asynchronous stuff with a critical section that a lot of your code depends on. This can lead to untraceable problems, like having exceptions with no way of starting point. Memory leaks are also a very potential candidate here, because sometimes when you use async, some of the contexts that are actually closed for you out of the box need to be closed and to be handled and coordinated manually. And when leaving this, you end up with, sometimes you can end up with out of memory. And the last one is memory visibility. I would say that this is also a lot of tricky. For example, if we take one lambda and we parallel stream it, and we have some exception inside the parallel streams, I would say that the stack trace would not be very readable, and we can be left with scratching our heads with what exactly is the problem. While if we did the same thing inside a for loop and we sacrificed parallelism, we would have much more cleaner code, and then everything would be a lot more readable and visible. And that was from me. I hope this was interesting for you, and that not a lot of you fall to sleep. If you have any questions, please feel free.
Thanks, Gjoko, for the always interesting presentation. So although our numbers went up to, I would say, almost 41, we managed to keep 34 until the end, which is a great success. And there are a few questions, and two, in fact, if I remember correctly, that was already asked. The first one is from Petar. Isn't viola dangerous to use with non-atomic operations like increment, for example? So yeah. Would you like to comment on that?
Yeah, exactly. You're right. I don't know why you're asking when you already know this, Petar. It is dangerous. Because if it's a non-atomic operation, as you already know or suspect, we can get a race condition, and we can get all data before incrementation, or we can get another type of problem, which is, as I said, volatile, is not considered that is 100% thread safe.
Great, thanks, Gjoko. So we have another comment from Stefan, which refers to the slide just before you started talking about Spring. You have more context than me. Similarly, like the merge sort. So you can just pick up that slide. It was about fork join tool. Yeah, fork join.
Well, actually, it's like divide and conquer. Yeah, I would say it's like merge sort, but more efficient. The idea is to traverse the tree with the recursive tasks, and then when we are only left with executable tasks, it uses pool in order to execute those chunks in parallel. So that's where the speed up comes, as opposed to plain recursive function. At the end, when you're executing the executable stuff in parallel. And there comes the speed up, of course, on the expense of memory.
Great, thanks. If you have follow-up questions on the answers that Gjoko just provided, just please make sure that you write down. So Nenad Jankovsky has a question. How can we handle exceptions in chained completable future? I have no idea what this means, by the way.
Yeah, sure. So basically, I think that there are, actually, I know that there are callbacks that actually can provide you with the exception handling. And I don't remember the name exactly, but they are part, I think they are already in that part of the Java 9. And that with them, you can actually create a call, and then on successful call do one thing, and then on exception do another thing. So I don't remember exactly the name, but the functionality is provided off the shelf.
Yeah, thanks, Gjoko. So far, another question. Aren't there exceptionally methods that deal with exceptions?
Yeah, exactly. Yeah, they are called, that was the fun name. Yeah, you're right. Exceptionally methods which deal with exceptions, which is actually a bit contradictory in the name, if you ask me.
So Peter has another question. Do you think that it's feasible to migrate an existing application to the reactive stack? Or is it better to use it only in new projects designed with reactive architecture in mind?
Yeah, that's a great question, Peter. Actually, I would go with the second approach. And why is that? Because First of all, if you have programmers or IT specialists, if someone is offended by the name programmer, if you have IT specialists that actually created the previous application, it would be a bit harder for them to switch the mindset. And also reactive is very interesting and very powerful, but only for a specific subset of the problems that the traditional Spring Boot stack solves. So if you had something that's reactive in nature, or if you had time to redesign and recreate your entire logic, I would say go for reactive. But in my experience and opinion, there is a very rare use case where you have logic for a service for entire application, only if it's a microservice. That's an exception. But otherwise, you almost always need to have some kind of blocking operation. And as I said, if you have at least one blocking operation, then you should consider abandoning the reactive stack.
Great, thank you, Gjoko. So far we don't have any more questions. We have 5 more minutes to spare. So I would just want to ask you whether you have some interesting examples, challenges related to concurrency that you have encountered throughout your work that you want to share, but very briefly, please. Gjoko, did you hear my question?
Yeah. I was waiting maybe if someone else wanted to say something, because they might be tired from hearing me speak. But yeah, it was a very interesting problem. It was directly related to concurrency. The use case was the following. We had a code that we put from development until pre-prod, till stage environment. And basically what the project did was take a bunch of DB records, then do a lot of computations, read from different databases, and after that write in a new database and migrate the entire data to the cloud. All of this was written in Spring Boot, I think. Yeah, and the interesting stuff was that even though on each environment they said that that we will not encounter bad data on production environment, we did. When it came to production environment, first let me give you a little bit of a context about the infrastructure. We ran like 100K of records from Mongo database. Then we chunked that with executor pool service to 5 different parts. And in each of the part, we would take and then chunk it to 10 or 20 records, and then make batch calls toward another endpoint, because we want to split everything up. And we did this by using lists partition from an array list. And then when we created everything with completable futures, we used the completable futures to get them and merge the successful ones, merge the bad ones, and log the bad ones, and etc. Now, when it came to production, because we gave the code on our call it from another side, from the client side to execute it, he thought that the code was slow. So what he actually did, he went into the code, and when the bad data was returned, instead of chunking it into a new array and connecting the data from all of the completable futures, he actually took the data and tried to remove it from the initial array. Now you can probably guess what happened when he removed it from the initial array. I don't know if any of you are aware, but if you use list partition, it actually partitions lazily. The next time you call the next item on the list, then it chunks it from the array. So because he in the initial, let's say if we have 10 chunks, when he removed the data from the initial array, 9 chunks remained, and then we got an exception like array index out of bounds. And because everything of that bonus points was inside of a thread and was not on the main thread, the debugger didn't log, the log didn't log anything, and we didn't have any exception. Basically, you end up with a code that runs well, but there is an error, and that error is never logged anywhere. So again, I would say be very careful when working and accessing data from multiple threads.
I think that was a great example and a great way to finish with our first tech and talk event here in Skopje. Thank you everyone for bearing with us for 1 hour now. If you find these talks interesting, please consider joining our group. Gjoko, thanks again. As always, you are willing to step up and share the knowledge, and I just wish all the best to you. For anyone else, if you have any questions regarding the group and if you want to step up and share your knowledge, feel free to join the group and contact us there. There is plenty of room on the internet for everyone. Bye-bye, guys.